In this segment, we're going to talk about neural machine translation. The nice thing about neural machine translation from our perspective in this course is that we've already seen all the ingredients we need in order to understand what a lot of the strongest models do. So we're going to start by kind of diving into results and comparing with the phrase-based translation paradigm that we've just developed here. So there's an annual workshop, or now a conference, called WMT, or the Workshop on Machine Translation, which has some data on English-French translation. And this is a fairly large amount of data, 12 million sentence pairs. And the classic phrase-based machine translation systems get around 33 blue on this task. And so this task is translating into French. So it's the opposite direction of what we've seen so far. And the other thing I'll say is that remember that there's a language model in phrase-based systems, so that this also uses additional French data. And so there was some work in 2014 on re-ranking these, re-ranking phrase-based outputs using LSTMs. This was one of the first successful approaches that integrated neural networks into the translation process and did a bit better. 3 blue points is a fairly substantial improvement, and this is definitely a better translation system. So then the first sequence-to-sequence modeling paper, which uses LSTM encoder decoders of the kind that we've built up already, got 30.6 blue on the same task. So worse than the phrase-based translation system and worse by a fairly significant margin. However, once you ensemble multiple of these sequence-to-sequence models together, you do get higher scores. You get 34.8 blue. And then it turned out that it only took people a couple of years to really get this approach tuned up well. So for the two major innovations here are attention and kind of correct handling of rare words, and that took things to around 37. So that basically kind of shows how well things can work on French, but this is a language pair with a lot of data and a fairly closely related set of a pair of languages. So we can also look at English-German, which is both a harder translation task and there's less data for it. But we still see that this system from Leung et al. Can get 23 blue, which is better than our classic phrase-based system at 20.7 blue. And I'll note that these blue scores are not comparable. So, English-German is a harder problem, and the systems are probably less good. But you can't directly, say that it looks way worse based on these blue scores, because it's really hard to normalize these across languages. All right, so from the perspective of English, translating into closely related languages like French and Spanish is fairly easy. German is also closely related to English, but some of the syntactic properties and the noun compounding and things like that make it a bit harder. Other Indo-European languages like Czech are also a bit harder. And then Japanese is one of the hardest languages, and as is Russian. Russian has very rich morphology. Japanese has very different syntax from English. And so, we can kind of think about a range of possibilities here. But by this point, people have gotten neural machine translation to be working well, even for these hard language pairs. All right, so just to kind of see an example, here's a fairly short example of a translation pair that the base model on the bottom, the most interesting thing going on here is that in a model without attention, this is about Bloom and Kerr, but it says Bloom said that he and Tina were still Unc. So the base model here kind of goes significantly off the rails and kind of spits out this thing about Tina even when it should be talking about Kerr. So the takeaway is that these models can hallucinate, and so that's something that we didn't see in phrase-based models, where it would never really produce that translation. Here's a more complicated example, and I show this primarily to show just how well neural seek-to-seek models with attention can do. So if we look at this best output here, because of the strict austerity measures imposed by Berlin and the European Central Bank in connection with the straitjacket in which the respective national economy is forced to adhere to the common currency, many people believe the European project has gone too far. This is a very long and complex sentence. It's a little bit run on. It's, the translation is much more tied to the German source input than we would necessarily like to have. Maybe it could be rewritten more simply. But regardless, this is a pretty good success and something that our model without attention on the bottom can't really do very well. All right, so the productionalized version of this from 2016, Google published a pretty substantial paper about their machine translation system, which is basically pieces that we've seen. It's an 8-layer LSTM encoder-decoder model with attention that is built on a word piece vocabulary ranging from either 8,000 words to up to 32,000 word pieces, let's say. So remember that these will contain some whole words, but also contain other subword units as well. All right, so that's it. That's something that we understand what's going on with all these pieces. And if you used Google Translate in probably 2016 to 2018, you were basically using this system. And so comparing to the numbers that we've seen before, this kind of pushed things a bit on English French and English German by about a blue point in each case. And they did some evaluation on English Spanish, and they found some very encouraging results, which is that their results, so the phrase-based system is in blue, which, Google had spent a long time building up a very strong phrase-based system here. So but they were still significantly beating it, getting much more high-scoring outputs with a score of 6 with this red the Google Neural system. And comparable actually to human performance. Now, the major caveat is that this is just on English Spanish, just on the data that they were looking at here in particular. This doesn't mean that translation is solved by any means. All right, so the next year after that paper came out, the Transformer paper made a fairly big splash and actually beat the results of the Google Neural system. And so on these language pairs, we see another couple point boost over the past results. And the way that these transformers work here is we have on the left here an encoder block, which we've seen before. And on the right here, we have a also stack of blocks that do self-attention over the output, the decoder, but also look back at the encoder. So you have this kind of complex interaction between these self-attention mechanisms that look just at the decoder so far, and then also at the encoder output. And this stuff's all stacked up and then goes on to predict a next word. So this is expensive in that in order to actually produce a translation, you have to run this whole big stack of layers to produce just one word, then feed that word back in and keep going, unlike the LSTM, which can kind of scroll through a sentence a little bit more naturally. But regardless, it works very well. And this was a big model at the time. Their biggest model had 6 layers and 1,000 dimensional vector for each token. So this is now relatively small by the standards of models like BERT, which range up to, and GPT, which range up to 24, 48 layers. But at the time, this was a lot bigger than many of the LSTMs people were thinking about. And to kind of see what sorts of things this can do, this is a visualization they have of their multi-head self-attention mechanism, which shows that basically the verb making here attends to a bunch of related things in the context. In particular, making progress more difficult, making the voting process more difficult. The model is able to attend to this more difficult thing and realize that that's related to this making verb, and kind of to make more difficult is something that might be translated differently and kind of non-compositionally necessarily in other languages. So they found a lot of nice properties of what the multi-head attention mechanism could do in terms of aggregating words into local phrases and things like that. So the last kind of point I'll say, a lot of the best systems in MT are big transformer models these days. The one thing I'll say is that people have also started using neural models for evaluation. So we'll talk about BERT in a future segment, but the basic idea here is that if we want to compare a reference and a candidate translation, rather than using BlueScore, we can instead use BERT to associate each word with a vector and then basically use a sort of cosine similarity to say how similar are these translations at this kind of deeper level. This correlates better with human judgments than BlueScore does, and really kind of gives us a possibly better metric that people are actively exploring these days. Another big challenge is dealing well with low resource scenarios. So low resource means, okay, we don't have millions of parallel sentences with giving us hundreds of millions of observed tokens in each language, right? So for a long time, the conventional wisdom was that phrase-based systems would work better when you have small amounts of data. And so recent work shows that neural machine translation can actually work pretty well here too. So this is some work due to Senric and Zhang, which shows that basically when you have only 100,000 sentences here, a well-tuned neural machine translation that incorporates a bunch of tricks like tuning the BPE vocabulary, tuning the batch size, and some other hyperparameter tricks can do as well as a phrase-based machine translation system. And of course, when you have a lot of data, the neural machine translation system is much better. So this kind of leaves us at the modern state of machine translation. People are exploring a lot of different ways of using neural models, exploring different architectures, different ways of doing pre-processing, different ways of building in notions like syntax, even inside neural models, etc. And one of the big focuses is how to do well on languages where we don't have as much data. That's the end of this segment.